Okay, so hi again. Today we'll be going through lecture 13. Yeah. This looks good. Okay, so the lecture is about contextual word representations and pre-training. This lecture is like it's a mix of a lot of things. Like we have ELMo discussed, we have ULMfit, and then there was BERT, there was attention. Like there were a lot of things that were discussed. None of them were talked about in detail, and that can be expected because these are the kind of topics which, like each of these things, will require a lecture or two to go into details of those. And this course, at the beginning of the course, we were told that this course is going to be more dynamic in a sense that, especially when it comes to the second part of the course, the way they have designed the classes, or they have chosen the topics, they have taken the students' input, like what they would like to do in the second half of the course. And depending on that, depending on the kind of inputs they got, they have chosen the topics. So that's what we see here. Like the students were asked about whether they would like the remaining lectures to be about transformers, BERT, question answering, and these are the kind of answers that they received from the students. Some of them said that they want to know more about new research and updates in the NLP. Some wanted to know more about the successful applications, stuff like that. And there was also a very brief discussion in this lecture, about how this course has been more about deep learning and neural networks rather than pure linguistics. So before CS224n, I think previously it was purely linguistics. And then with the recent years, how deep learning has emerged and how using neural networks, NLP has seen rapid progress. So for that reason, they have kind of clubbed both the things. So this is about some assignments. So this is the plan for this lecture. The first part is going to be about word representations, and then we'll see about ELMo and ULMfit, and then we'll go through some slides about transform architectures, and finally about BERT as well. We got started with the course.
Sorry, just a quick question for you. Did as part of the as part of this overview and so on, have you all attempted the assignments?
We have discussed some of the assignments before, but we haven't really taken up. I think we did assignment 1, 2, and 3, and coming to 4 and 5, we haven't done it yet.
Okay, great. Thank you.
Sure. So I think there are people who are working on assignments. It's like if you have done any work on assignments, like even if you didn't totally finish the assignment, if you have something to share with the group, you can feel free to join and present. So yeah, so we got started with understanding how the text can be represented using numbers, but that's nothing but using word embeddings for representing words and textual data. So for that, we used word2vec, glove, and in the previous lecture, we mentioned fast text as well, though we didn't really get into the details of it. So these are quite often used methods for getting the word embeddings. But there are some problems with these kind of methods as well. Here is some history about pre-trained word vectors. So what are pre-trained word vectors? Right now, let's say we have glove or word2vec. We have pre-trained models these are the things that are already trained on a large text corpus. And now if let's say I want to use, I want to get some word embeddings or the vector representation for my text, I don't necessarily have to start from training my own neural network from scratch to get my word embeddings. There are things like word2vec and glove, and also now we have BERT embeddings as well, which give us readily available word embeddings. This started in the year 2011 or 12, where back then the state of the art was like, it was giving scores of something like 97.24. And the first one that we see here, that got nothing to do with neural networks. It's a totally different traditional kind of an approach. And then when they tried using supervised neural networks in 2011, they were not really able to produce results that were as good as the traditional counterparts. As we can see here, the state of the art back then was 97.24 for POS, part of speech tagging, and for NER, named entity recognition, it was 89.31. When they tried to use neural networks for that, the scores or the results that they found were these 96 and 81, which almost like 9 to 10. When it comes to NER, it's like almost 8% behind. For POS, it's almost close. But something that they observed is that instead of going with supervised neural networks, when they tried unsupervised pre-training followed by supervised neural networks, they got very comparable results. As we can see here, we have 97 and 88. And for this, they added something else, like some handcrafted features. You can, that further increased.
We've lost you.
Hello?
Joseph, can you hear audio?
I can still hear. Can you hear us?
I can hear you, yeah.
Or Christine?
Yes, can you hear John?
I think maybe.
John may have lost audio. Let me type him a quick note or something.
Yes. Shall I continue?
I think he's maybe he lost audio at his end.
Okay. I'm properly audible, right?
Yes, I can hear you.
Okay. Maybe we can wait for John. Once he confirms that he can hear us.
Yeah, sorry, I'm back. I don't know why my headphones suddenly stopped working, so I just pulled it out and it's fine now. My apologies.
No problem.
Okay.
That's fine. Yeah, so we were discussing this slide. I hope you were. I hope.
Yes, I caught most of that. Yes, thank you.
Okay, sure. So by making some changes to, like, when they didn't really get that good results with supervised when compared to the state of the art back then, and then they tried with unsupervised, and they also added some handcrafted features, and then they started having comparable results to that of the state of the art. But the problem was with that is that they had something like 130,000 word embeddings that they used some Wikipedia text and using some 100-unit hidden layer that you can think of it as an embedding vector with 100 dimensions. And that took almost 7 weeks for training. So that's a lot of time, which is not really optimal. So here is another chart that compares how the things have changed. Like when Chen and Manning, for the dependency parsing, with and without pre-trained, we can see the results here. Like by using pre-trained networks, there is a slight improvement in the results that were produced. So though they
Sorry, just a question. Forgive my ignorance.
please go on.
Yeah, so forgive my ignorance. In the previous slide, you were referring to POS. It's been a while
Yes.
since I looked at NLP. Can you remind me again what POS was?
Yeah, so POS is part of speech tagging. Like given a sentence, you tag every word in it with its part of speech. That's an NLP task. That's one of the tasks that is used for benchmarking the architectures of the models. Like let's say we have a sentence like, we are in CS224, like we is a pronoun. So it's that kind of classification.
So whether you're getting the nouns and adjectives right, or what? How are you measuring the accuracy?
Oh yeah. So coming to that, this may not be the exact answer, but the way it works is for POS tagger, like you have a sentence with its actual POS labels. Like again, going back to the same example, we are in CS224. If that's our training data, that will have its own labels. Let's say we is this, like it's a pronoun, CS24 is a noun, something like that. And then when we have these models and we pass the data to these models and we get some output, and these, the expected outputs and the generated outputs are compared, and that's how the accuracies are reported.
Okay, great. Thank you.
No problem. So yeah, training from scratch is one possibility, but that would take a lot of time and it would need a lot of resources. Like if the task that I am trying to work on can leverage an existing pre-training model, it's always suggested to go with that, because the kind of pre-trained embeddings that we have, whether it's Glove or Word2Vec or the word embeddings that we have from BERT model, they must be good enough at least to get started with our task. So it's only when our task is something like which is very domain specific and we may not have a data set for that, maybe then in that case, we can go for training a model from scratch and generating our own word embeddings. So that's one way of doing it. And the other way of doing it is to simply use a pre-trained model. So what about unknown words? We touched upon this even in the previous two lectures. So when you're trying to use word embeddings that are pre-trained, they're as good as the data sets on which they're trained on. Now, if let's say I have a data set which is from some news data, the data set which is collected from some news channels and news articles, and now my task is to work with sports data. So what if these two are totally different? And in that case, what happens is the data that we have might have a lot of words which are not present in the training data that we have used for our pre-trained models or for generating the word embeddings. In that case, we will not get the best of the results. So there are some ways to handle it. As discussed in the previous lecture, using character level embeddings is one way of doing it. That way, you're not strictly dependent on the vocabulary of your data set. And here are some tips to work with unknowns. Like let's say you have your text corpus, and then you have a frequency distribution of each of the words in your vocabulary. And what you can do is you can say that if there's a word which occurs less than 5 times, I'm just going to mark it as UNC. UNC stands for unknown. And then instead of blindly using that as an UNC, you give it a word vector. So just like different words like apple, cat, and dog will have their own word embedding, even UNC will have its own word embedding. So that way, whenever there's a word which the model cannot identify, it will give it or assign it the word embedding for the word UNC. So that's one way of doing it. But the problem here is that this way we are classifying, or this way we are assigning the same word embedding for all UNCs or all unknowns. Like let's say if we have 10 unknowns in our data, when I'm saying unknown, it just refers to a word which is not present in the training data, a new word. So if we are giving the same word embedding for all the unks, then we'll not really be able to distinguish between different new words. So that's the problem. So the solution for that is to use character level models. So what happens at character level model is that when given a word like, let's say, computer, what it does is it generates character level embeddings for every character. So for the word computer, it generates embedding for C, for O, for M, so on. So this way, the model is not really dependent on the word. Instead, it can generate embeddings using every character in the word. So that's one way of handling it. So let's say we are trying to build a question answering system, and the user might input any word. The word, there is no guarantee that that the user uses words that the model is trained on. So the system has to be robust enough to handle words which it has not seen before. So in such cases, it becomes very critical to handle unknown words. So here it says for the words, assign a random vector. So this is one way of doing it. If using character level embeddings is if you don't want to go with that, then what you can do is for every unk or for every unknown word, you can assign a random vector. And that way, every new word will have a random vector embedding, which is going to be different. So that way, we'll still be able to differentiate among different new words or unknown words. Yeah, so this is kind of a summary about for what all we have discussed so far. When we are going with word level embeddings, let's say you're using something like word2vec, and no matter how many times you give the same word to it, the word embedding that it generates is always going to be the same, and that's how you would want it to be. But there will be a problem in a case where, let's say, the sense or the semantic meaning of a word changes depending on the context in which it's used. So in that case, these embeddings may not be really helpful. Now, let's say we have words which mean different in different contexts and different situations. So these word embeddings won't really be helpful in such cases, because no matter they always use the same embeddings. But if we can get into much, if we can have a fine-grained or much finer word embeddings, that would be really helpful in those kind of situations. So that's what we see here. We just have one representation for a word, but words have different aspects. The semantic meanings differ, the syntactic behavior. So all these kind of things differ when the word is used or spoken in a different context.
Sorry, just a quick question here. So
Sure.
when I talk about representation for a word, right? So I know what semantics are. What does it mean by aspects and syntactic behavior?
Okay, so I think, but words have different aspects. So if I'm not wrong, aspects here simply refer to the fact that the word could mean, different depending on the context. Now, let's say, let's simply pick a word like, I think this was given in the lecture, like star. When you're using the word star, it could be something that you're referring to a star in the sky, or it could be something like a movie star or a pop star or something like that, right? So depending on the context or the situation in which you're using the word, its aspect or its semantic meaning is going to differ, which comes to us pretty intuitively. Like, nobody has to explain, at least not in every situation, that somebody has to explain it to us what exactly they mean when they say something. But when it comes to something like a program, it's not that easy. That's what it means when we are referring to different aspects or including semantics.
Great. Okay. Thank you. Yes. Thank you.
Sure. Yeah.
So is the thinking that words with different connotations or meanings should have different embeddings? So it's spelled the same, it's the same word, but it has a different meaning. It should have a different embedding. Is that what we're saying?
It may mean that different parts of the embedding needs to carry different values to convey both meaning, to contain both meanings, so that the appropriate one can be chosen. I mean, that's how it turns out later.
Yeah. So when we have, let's say, 3-dimensional word embedding vector, each dimension contains some sort of information that could refer to some semantics. So this, I think, is leading to some confusion. So if we go back to the very first lectures in the course, these things were discussed back then as well. So when it comes to word-to-vec, when we have these kind of ambiguous situations where the word could mean different things, I'm trying to recollect this, these plots where we have plotted the word embeddings as 2-dimensional points, and depending, like let's say the word new, right? So when you're using it with New York, it means that it's a city. Or by simply using new, it means that it means totally something which is totally different. So the word embeddings do capture these sort of information, but having said that, we still have this problem with that. Did that make sense? I'm not sure whether I did.
I think I probably need to read some more, but I'm okay. We can keep going.
Sure. Maybe that we can take that as a point, to explore, and do share with us if you find something. Okay. Yeah. So what does a language model do? So to put it simply, the language model tries to predict the next word that comes after the given previous words. So that's what a language model does, like predict the next word. So if you see here, we have the sentence like my favorite season is spring. For each of these words, we have the word embeddings here, and that is being passed through some hidden states and some network. So the point here is that whatever the representation that we get, the context or the vector representation that is generated from this network, that is very context specific. So that, what does that mean? It's like my favorite season is spring. Each of these words and the final feature representation that is generated is very specific to this data or to this example. So that's the problem with language model. Like, more than saying that it's a problem with language model, that's how the language model works when used in this way. So the representations that are produced from these kind of models are very specific to the data that is fed into them. So this is one paper called TagLM, which was before ELMo, and yeah. So here what we do is we are taking some unlabeled data, and then we are generating the word embedding model from this. We have two things here. One is a word embedding model, and then we have a language model. The example here again is the same. New York is located. What we're doing here is that we first pre-train word embeddings. That's what we are using here. And then we get the word embeddings for each of the words. Yeah. So here we have the unlabeled data. Using that, we are generating our word embedding model and the language model. Once we have them ready, we have our actual data here. The input, New York, is located. And using the word embedding model that we have created here, we are going to generate the word embeddings for these words, for the input sequence. And that is what we are going to pass to the sequence tagging model. So the output of this is going to be New York, what block and eloc. These are the two tags that we have here. What that means is that New York is a location, and this, what we have here is block. Here it means beginning of the location. So this is where the location, the word begins, and eloc means this is where the location word ends. So this is how we are going. These are the kind of tags that are generated from this sequence tagging model. This is just an example to show how TagLM works, like what are the components of it. So instead of starting with a supervised, so the entire point here is that we try to use something like some semi-supervised approach instead of a supervised approach. And how are we doing that? We are getting started with an unlabeled data. Yeah. We are getting started with an unlabeled data, and then we are using these two things, word embedding model and language model. Using those two things, we are generating the word embeddings and the language model embeddings, and then we'll finally get the outputs out of this model. So that these are the components of the TagLM architecture.
So I've got a question for you. So if I understand it correctly, the language is the language modeling the one that will try and predict the next word?
Yeah. So there are two things here. The purpose of word embedding model is simply to give a numerical representation of the text that is passed to it. So that's all it does, is it takes a word and it gives out a vector or numeric representation for that word. It got nothing to do with predicting the next word. So it's the language model's objective, or the task of the language model is to generate the next word.
Okay, I think what I don't understand is what purpose does the begin lock and end lock serve? Because I don't see why it needs. I don't know what it's doing.
Okay, so I think there are like this. One thing is that these are the components of the TagLM. That's the main objective of this slide. And then the task that it is trying to do here is something called sequence tagging model. So if I'm not wrong, what it does is it is trying to tag the input sequence, saying, okay, the first word here is the beginning of the location. Here, New York put together is a location. And then what this model does is it says that, okay, we have the word New York, and new is the beginning of the location, and York is the ending of the location. So it's that very simple model that is trying to tag locations. It could be.
Okay. To think about that a bit more. Okay, thank you.
Sure. Here's a more more detailed representation of this model. So what we have here is on the right we have the language model, and here we have our token representation. So New York is located. That's the input sequence that we're giving it. And then we have some RNNs here that are generating the token representation. And these token representations are being passed to some bidirectional RNN. And we have two of them here, bidirectional RNNs. And the final output of them is passed to a dense layer. And then we have the same thing like block and eloc, beginning and ending location. So it says sequence tagging. I didn't really like the lecture, this particular lecture has been like, in terms of the things that it has covered, it has been dense, but the things were not really discussed in detail. But again, it's something that was mentioned, like it was mentioned in one of the previous lectures that do not expect the second half of the course lectures to be more in depth. It's left to the students to explore and learn them better. I haven't done that part yet, so I'll be doing it in the next few days. So here we have the language model. This is a pre-trained language model, which means when you pass the input, it generates the outputs ready-made. So you're not really doing any kind of training here. So now we have named entity recognition. So named entity recognition is another NLP task. What it does is, given a sentence, it tries to classify each of the words into some different entities. Like, it could, given a sentence, it might say that, okay, this word is a person, this word here is a location, and this word here is an organization. So this is an example sentence here, the decision by the independent MP Andrew Wilkie. So Andrew Wilkie in blue. So what does blue mean here? Blue means that it's a person. And then we have another word tag, which is labor, and that is nothing but organization. And then we have something in here, when after the 2010 election, 2010 is nothing but date. So this is what named entity recognition does. Given a sentence, it tries to identify the words to which class do they really belong to. Here's another results benchmark. What we have here is, by the end of 2017, we have TagLM, the paper or the architecture that uses LSTM and bidirectional language models for tagging sequences, and that gave the best results of 91.93, beating 91.21 from the previous year. I actually wanted to go through a couple of blocks. So as we see here, once we're done with TagLM, there was a brief discussion about ELMo, embeddings from language models. And again, we have come back to the same architecture. This is about ULMfit. You must have heard about it if you have taken any of the FastAI recent courses. This is just about how much time it takes to train each of these models. ULMfit takes like 1 GPU a day. GPT and GPT-2, you must have heard things about it, like OpenAI, when it first came with GPT, they initially said that they're not really going to release the full model, not knowing how it would be used by the people if it is like openly and totally released. And here is one example of a text that is generated by GPT-2 model. This is like a human written sentence. In a shocking finding, scientists discovered a herd of unicorns living in a remote, something like that. And what we have below is a mission written text generated by the GPT-2 language model, which actually looks very related to what we have and what is written by a human. There was a lot of buzz on Twitter and Reddit when GPT was when OpenAI has announced that they're not really going to release the entire model. So transformer will attention, multi-head attention. I want to share a blog. I want to quickly go through that. Hope you all can see the browser now.
Yes.
Okay. So in the later part of the lecture, there are like so many things that were covered. There was some discussion about transformers. There was something about attention. There was something about BERT. All these are like somehow related to each other. J. Ollemersberg is something that we keep referring to. He writes very well and with all good illustrations. We'll see here what, before going to the transformer, let's quickly go through what attention is. So when we have a sequence-to-sequence model is nothing but it takes an input which is in the form of a sequence, and then it generates an output which is also a sequence. To give an example, machine translation is one task that can be solved using the sequence-to-sequence models. What we have here is we have this input sentence in some language here, 3 words. They are being passed to our sequence-to-sequence model, and there is some processing that happens here. We'll see what that is, and then it finally outputs the translated sentence in the target language. Here the target language is English. Now let's go a little deeper. So this again is the same thing. Instead of now we have some better representation of the black box, or what we have here is sequence-to-sequence model, the same thing. So the sequence-to-sequence model contains 2 components. One is the encoder and the decoder. So the encoder first takes the original input. In this case, we have the source sentence in some language that gets passed to the encoder, and the encoder generates some context or some representation of this input sentence, and that is passed to the decoder, and decoder finally outputs the result. This is another visualization of it. Now we come to some details of it. So the context is nothing but, again, it's a vector representation. So whatever we are dealing with inside the neural network, we know that a neural network cannot understand alphabets or letters. So whatever happens inside it, it has to be numeric, some sort of numbers. So this is what that gets passed from the encoder to the decoder. Here we have 3 words, and what we see here, each row here is a vector representation for each of the words. So for the first word here, we have this word embeddings, and for the second word, we have these word embeddings. So these are going to be the inputs for the encoder. This is the recurrent structure of an RNN. You have a hidden state here. You pass an input to it. It gets another input from the previous hidden state, and both of them are put together, and it generates 2 things. One is an output, and the other one is the hidden state here. So here, what's happening is that we have 3 words in our input sentence. They're being passed to the encoder. The first word has gone in, and it generated a hidden state for this, which is nothing but this hidden state contains information related to the first word. And next, we have another word that goes in. The second word has gone in, and it has generated its own hidden state. And
what's the purpose of the hidden state?
So hidden state is nothing but, if you're familiar with recurrent neural networks, here, this is what we have in a recurrent neural network. We have an input. From that example, this input is nothing but the word itself, one word. Yeah. So that word goes into the recurrent neural network. This is the hidden state. Hidden state is nothing but the processing unit. Is that clear?
Yeah, I'm just trying to answer. When you say processing unit,
processing unit is a very vague way to say it. So instead of that, okay, let me add a little somewhat to that. So if you're familiar with CNNs, right? Convolutional.
Yeah, I'm familiar with CNNs, yes.
Yeah, so now let's say we have an image. That image, we are going to convert that into a 2D matrix, a matrix, right? A two-dimensional matrix. And then that we are going to pass through some first layer, right? And there, what you have there is there is some convolution that happens on the input image, and that generates some map, right? The output from the convolution, right?
Yeah.
Yeah. So its equivalent is what we have here, which is nothing but hidden state. So hidden state is nothing but here we have this input here is a word embedding, right? You can think of this as a matrix when comparing that to images. This we are passing through the first layer. You can think of this as the first layer. It's not here, but what we have here is a weight matrix, right? Just like we have weight matrices or the filter maps in CNNs, we'll have a weight matrix here, and then we have the regular, the word embeddings get multiplied with the word matrix with the weight matrix, and the output of that will be the hidden state, right?
Okay.
So
okay, no, sorry. I guess So I'm coming to NLP from the CNN world. So hence
okay.
there's a few gaps. But what's the reason why we have this? What's the reason why we have this like almost like a feedback loop? That's the bit I guess I don't understand.
Yeah. So here you can. So this is for input 1, right? So
right.
Then you have this is for first word. So then you have another word. The structure remains the same. What the feedback loop here means is that it's the same thing that's repeated again and again for all the input words.
The weight matrices are shared is what that represents. So as you go through the word sequence, you don't use a new matrix every time. You reuse the word matrix or the matrix for the same matrix for the entire sequence of words. That's what the circular thing represents. So it's kind of important or critical to understand the recurrent neural networks, because that's the foundation, much like CNNs are the foundation for visual processing, RNNs are the foundation for word processing. So it's kind of key because the circle there represents the shared matrix, which is what RNNs use.
Okay, great, thank you.
I'm just trying to find one block. RNNs. So this is one way of representing an RNN unit. I think if you see the expanded one, that would be clear for you. Okay, I think it's not. I'll share that in the channel. Please go through that. Maybe that would clear this for you.
Thank you.
And also go through this blog, ULMers. They are very good. Like they have these good illustrations and they explain things pretty well.
Okay, great. Thank you.
Yeah, no problem. So coming back to this. So for every word, you're going to generate a hidden state. So what it means is that for every word, you're having some sort of representation. So this is for the second word. The same is repeated for the third as well. So now, what you have to notice here is that what's being passed from the encoder to decoder is the hidden state, the final hidden state. So what about hidden state 1 and hidden state 2? They're not really being forwarded to the decoder. So that's one problem with that's one problem that we have with model that doesn't use attention. So now, what happens with attention? When we're using attention, here, if you see, all the three hidden states are being passed from the encoder to the decoder. So that's the main difference between having and not having attention in the model. So when you don't have attention, you're simply passing the final hidden state of the encoding unit to the decoding unit. But with attention, what you're doing is you're actually passing all the hidden state representations to the decoder. And how will that help? Yeah, we'll see that here in the transformer. So transformer is nothing but it's a model that uses attention, and by doing that, they have produced better results, and they also boost the speed at which these models can be trained. So here again, the same thing. We have an input sentence in some source language that is being converted into the target language, machine translation. We have the input here that is being passed to an encoder, and the output from the encoder is being passed to the decoder. The decoder will finally produce the translated sentence. So this is a very simplified representation of what happens inside, but normally what you have inside an encoder is a stack of different encoders. Here we have 6. I think this is taken from the paper, Attention is All You Need. So here we have the initial input layer here that is being passed to the encoder. The input for the first encoder is going to be the word embeddings of the words that we have, of the words of the input sequence. And the input for the subsequent encoders are going to be the output that is generated from the previous encoder. So once you're done with all of the encoders, they are passed, the output of the final encoder is passed to all the decoders, and finally we get the output. So now let's, so how will each encoder look internally? So inside an encoder, we have 2 things. One is self-attention, the other one is feed-forward neural network. So self-attention, that's what we discuss attention now. Let's see how it comes into play here. So we have an encoder, and in an encoder we have 2 things, self-attention and feed-forward. But when it comes to decoder, we have another extra layer called encoder to decoder attention. We have 3 words, 3 inputs, 3 input words here in the input sequence. We generate the word embeddings for them here. This 4-column row represent the word embeddings that is being passed to self-attention, and you have an output from that is being passed to feed-forward. Yeah, so what exactly is attention? To simply explain it in plain English. Now, let's take this example. The animal didn't cross the street because it was too tired. Now, what exactly is the word it referring to in this sentence? For us, it's pretty easy to say that it here represents the word the animal, right? But for a machine or a program to do it, it's not that easy. So that's where attention comes in. What attention does is it somehow gives a score for the current word. Now let's say we are currently currently processing the word it. Then what it does is attention gives some sort of score for how it relates to every other word in the sentence. So as we can see here, the word it has some relations with all of these words, but here we see that it is associating most with the animal. And then this is one example. Queries, keys, and values. So we have 2 more minutes left. I'm not sure whether we can continue or not, because if we do, and what time does the next study group start? Is it immediately, like?
Yeah, unfortunately it's at 8:30.
Oh, okay. I'm not sure whether they'll be able to start if we keep continuing.
Right, okay, well, thanks a lot for your time. I do appreciate you taking the time to prepare this for us, so thank you.
Sure, no problem. Maybe we can continue this next week.
Yeah, I'd like that. I'd like that. I was hoping maybe we could do a deeper dive into things like ULMfit and ELMo and
Yes.
BERT. So, but
Sure.
see you next time. Thank you so much.
Sure. Yeah. Thanks all for joining.